Hello students, let's continue the chapter electricity. The last topic is left and the topic is electric power. You may just study power in class 9. In class 9, power was defined as the rate of doing work, that is, power is equal to work done upon time taken. Work done upon time taken. And in the same class 9, you might have studied one more definition of power. Power is also defined as the rate of consumption of energy, that is, energy consumed upon time taken. For electric power, this is the more appropriate definition. Electric power of a device is defined as the rate at which that device is consuming electrical energy. So, E stands for energy consumed, T stands for time taken. We know that energy is measured in joules and time is measured in second. So, it will be joule upon second. But joule per second is given another name, and that is watt, and it is represented by capital W. So SI unit of power is watt. SI unit of power is electric. Now let us see. There are some more bigger units of electric power. Watt is comparatively a small unit. So other bigger units of electric power are kilowatt, and 1 kilowatt is equal to 1000 watt. 1 kilowatt is equal to 1000 watt. Now using this from formula P is equal to E upon T, we can find out the total energy consumption. Since P is equal to E upon T, E will be equal to P into T. That is, energy consumed is equal to power into time. Power is measured in watt in SI unit and time is measured in second. So it will be watt second. But watt second is a very small unit. For measuring the electricity consumption of a house, or establishment or factories, if we can measure it in watt second, it will come in many lakhs. So, due to the inconvenience, the electrical energy consumption is not measured in watt second. Even though this is the SI unit, it is not used for commercial purpose. In our homes, factories and establishments, total energy consumption of a month is measured in kilowatt hour. Kilowatt hour. So, commercial unit of electrical energy is kilowatt hour. So you can see from here, kilowatt hour means power is to be taken in kilowatt and time is to be taken in hours. We know that in our homes or in all the places, electrical appliances are working for many hours. So we are taking time in hours and power in kilowatt. So commercial unit of electrical energy consumption is kilowatt hour, or it is simply known as units. When the electric meter reader comes and give you the electricity bill of a month, we simply say this many unit is the consumption of electricity for this particular month. So in common language, when we use the word unit, how many unit of electricity is consumed in a month, it really means that much of kilowatt hour is consumed. So kilowatt hour is the commercial unit of electricity. Now let us convert this kilowatt hour into SI unit. SI unit of power is watt. So 1 kilowatt is 1000 watt. And 1 hour is to be converted into second. So it is 60 into 60. Now it has become SI unit, watt and second. So SI unit of energy is joule. 1000 into 60 means 6 into 6, 36. 1, 2, 3, 4, 5. This is the conversion of kilowatt hour into joule. Or we can write it as 3.6 into 10 raised to 6 joule. So 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule. This is the conversion of commercial unit into SI unit. Normally, as I told you earlier, for practical purposes, electricity is measured in kilowatt hour. This kilowatt hour is nothing but in our local language or in our usual language, when we say the consumption of electricity for this month is 200 units, it means 200 kilowatt hour. Now, electric power has some more definitions. We have already studied the formula P is equal to VI. This is also a formula for power. What is this? V for potential difference, I for electric energy or electric current. So this is another definition for power. So how can you define 1 watt of power? When there is a potential difference of 1 volt across the two ends of a circuit, which produces an electric current of 1 ampere in that circuit, the electric power consumed by the device is said to be 1 watt. For defining anything in 1, you have to make the quantities that are given in the formula to be 1, 1. So when we put V is equal to 1 and I is equal to 1, P will become 1. So how can you define 1 watt power? When there is a potential difference of 1 volt across the two ends of a circuit, where there is 1 ampere electric current, then the power consumed by the device connected to that circuit is said to be 1 watt. Now using Ohm's law, if I change V, then we know that V is equal to IR. So IR into I, it will become I square R. So this is another formula for power, and this is another formula for power. So power can be defined in many ways. It is W upon T, it is E upon T, it is V into I, and it is I square R. So all these are the definitions of power. But when we come across electric power, these are the formulas used. It is the rate of consumption of electric energy by any device. So E stands for electrical energy consumed and T stands for time. So it is energy consumed per second. Another formula is V into I. Another formula is I square into R. So this was the last topic of the chapter Electricity of Class 10 Physics. I hope all the points are clear to you. Go through the topics once again, go through the videos once again, and if you have any doubt, then you can ask in the comment box. Now I am starting with the question answers of the chapter. Now let's discuss the questions that are given in the chapter Electricity. There are some questions given in between the topics of the chapter, and there are some questions at the end of the chapter exercise. I am going to discuss each and every question of this chapter. Most of the points, most of the questions are already been discussed in my lecture, so it will be a repetition, and some questions are new, so you please take care of both the type of question. Page number 200. You can see the first question on page number 200, and the first question is, What does an electric circuit mean? I have already taught. An electric circuit is the continuous and closed path through which electric current flows. I repeat, an electric circuit is a closed continuous path through which electric current flows. Second question, define the unit of current. Define the unit of current. There are actually two parts in this question. Define the unit of current means you have to say what is the unit of current and then you have to define it. So the first part of the answer is the SI unit of current is ampere. The SI unit of current is ampere. Now you have to define 1 ampere. And what is 1 ampere? The formula for I is Q upon T. So SI unit of electric current is ampere. So how can we define 1 ampere? When 1 coulomb of charge is flowing through a circuit in 1 second time, then the electric current produced in that circuit is said to be 1 ampere. I repeat, the SI unit of current is ampere. Now, definition of 1 ampere. When 1 coulomb of charge is flowing through a circuit in 1 second time, the electric current produced in that circuit is said to be 1 ampere. Question number 3. Calculate the number of electrons constituting 1 coulomb of charge. This was also taught by me in the previous video. Number of electrons present in 1 coulomb of charge. We know that charge of 1 electron is 1.6 into 10 raised to minus 19 coulomb. So, number of electrons needed for 1 coulomb is equal to 1 upon 1.6 into 10 raised to minus 19. 1 upon 1.6 into 10 raised to minus 19 is approximately 6 into 10 raised to 18. So number of electrons needed to constitute 1 coulomb charge is equal to 6 into 10 raised to 18. So in page number 200 there were 3 questions. Now page number 202. In page number 202 also there are 3 questions. Question number 1. Name a device that helps to maintain a potential difference across a conductor. Name a device that helps to maintain a potential difference across a conductor. There are many devices that can produce a potential difference across the two ends of a conductor. They are a cell, a battery, or a generator. If you connect the two ends of a circuit to a cell, there will be potential difference across its two ends. Now many cells connected together is called a battery. A battery can also do the same thing. A generator can also do the same thing. So a cell or a battery or a generator is the device that can produce potential difference across the two ends of a conductor wire. Question number 2. What is meant by saying that the potential difference between 2 points is 1 volt? What is meant by saying the potential difference across the two ends of a wire is 1 volt? Already taught. Potential difference V is equal to W upon Q. Now define 1 volt. What is W? Work done. What is the unit of work done? Joule. What is Q? Quantity of charge transferred. What is its unit? Coulomb. So how can you define 1 volt? When 1 joule of work is done to transfer 1 coulomb of charge from one point to another point, the potential difference across these 2 points is said to be 1 volt. I repeat, I hope all of you remember my previous class. When 1 joule of work is done to shift or to transfer 1 coulomb of charge, 1 coulomb of charge from one point to another point, then the potential difference across these 2 points is said to be 1 volt. Question number 3. How much energy is given to each coulomb of charge passing through a 6 volt battery? I repeat the question. How much energy is given to each coulomb of charge passing through a 6 volt battery? You are asked to calculate the energy for what? How much energy is given to each coulomb of charge? Each coulomb of charge means Q is equal to 1 coulomb. And you are given the potential difference is equal to 6 volt. Then what is the energy? We know that energy is equal to work done. So actually we are asked to find out the work done in this question. We know the relation between work done Q and V. V is equal to W upon Q. Therefore W is equal to V into Q. Here V is equal to 6 volt and Q is equal to 1 coulomb. So W equal to 6 into 1, 6 joule. And work done is numerically equal to energy. Therefore, energy is equal to 6 joule. So the answer is 6 joule of energy. Now the next page number is page number 208. Page number 208. First question. On what factors does the resistance of a conductor depend? We have seen this topic in detail. On what factors does the resistance of a conductor depends? Before that, I am going to write the formula for resistance once again. I hope all of you remember. Resistance R is equal to rho into L upon A. So the resistance of a conductor depends upon these 3 factors. What are they? Rho is the resistivity. And what is resistivity? Resistivity of each material is a constant. So the first point is material of the wire. Second, L. What do you mean by L? Length of the wire. Now, what is the third point? Area of cross section of the wire. Area of cross section of the wire, or it is also known as thickness of the wire. And I may add one more point to this answer, and the fourth point is temperature. Because temperature can also affect the resistance of a conductor. When the temperature increases, resistance also increases. Now, how do they relate to each other? That is not the part of this question, but for your knowledge I am explaining. Material, rho means resistivity. Resistivity of a material is constant, it never changes. If rho value is least, we say that is the best conductor. Rho value of silver is the least, so silver is the best conductor. We have already seen it. When length increases, R increases. When A increases, R decreases. Only to thickness, R is inversely proportional. and the remaining two are directly proportional. L and temperature. When length increases, resistance increases. When temperature increases, then also resistance increases. Rho is constant. And with A, it is inversely proportional. So, finally we can say the resistance of a conductor depends upon four factors: material of the wire, length of the wire, area cross section of the wire or thickness of the wire, and temperature. Now, question number 2. Question number 2 is, will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source, and why? Answer is very easy. Current flow more easily through a thick wire because resistance is inversely proportional to area cross section or thickness. When the thickness of the wire increases, resistance decreases. Resistance less means it is easy to pass through the wire. So, electric current passes more easily through a thick wire. Question number 3. Let the resistance of an electrical component remains constant. Resistance remains constant, while its potential difference across the two ends of the component decreases to half of its former value. V become half, R become same. What change will occur in the current flowing through it? Simple question. When V become half and R remains constant, what will happen to I? I hope all of you remember the formula V is equal to IR. Ohm's law states that V is equal to IR. Now in the question it is given R remains constant and V will become half. Then what will happen to I? I will also become half. Because V is equal to IR, or in other words we can say V is always directly proportional to I. So if V become half, I will also become half. If I become half, then V will become half. V and I are directly proportional. So if R remains same, then whatever happens to V, same will happen to I also. So if V become half, I will also become half. Next question. Why are coils of electric toasters and electric irons made of an alloy rather than a pure metal? Yes. We know that the coils of electric toasters and electric iron are made up of alloys. There are two reasons for this. Number 1, alloys have higher resistance than pure metal. Alloys have higher resistance value than pure metal. So what is the advantage? If the resistance is more, it will produce more heat. When the resistance of a wire is more, it will not allow electricity to flow through it easily. It will oppose the flow of electric current through it. When it opposes more, then more amount of electricity will be converted into heat. So remember, the elements of electric toasters are made up of alloy. Number 1 reason, alloys have higher resistance value than pure metal. Number 2, pure metals react with atmospheric oxygen very easily and will be converted into metal oxide. And there is a possibility that these elements can get damaged, or it is called corrosion of the metal. Pure metals can be corroded easily because it reacts with atmospheric oxygen. Whereas alloys do not react directly with oxygen. Most of the alloys do not react with oxygen and they do not get oxidized. So 2 points. Number 1, alloys have higher resistance value, so it will produce more heat compared to pure metal. Number 2, metals normally react with atmospheric oxygen and get oxidized. Getting oxidized means there is a possibility of destroying it at a faster rate. But alloys have comparatively less affinity for oxygen, so they do not get oxidized and do not get damaged. Last question. Use the table given in the book. Table 12.2 to answer the following. Number 1. Which among iron and mercury is a better conductor? Iron and mercury, you can see in page number 207 there is a table given of raw values and you are asked to find iron and mercury which is better conductor. Iron, the raw value of iron is 10 into 10 raised to minus 8. And where can you see mercury? Mercury is below iron, 94 into 10 raised to minus 8. So, the raw value of iron is lesser than that of mercury. So, which one is better? Iron is a better conductor. Lesser the value of raw, better the conductor. So, raw value of iron is 10 into 10 raised to minus 8. Raw value of mercury is 94 into 10 raised to minus 8. Since the raw value of iron is less than that of mercury, iron is a better conductor. Second part, which material is the best conductor? We have discussed it several times. Silver is the best conductor because the raw value of silver is least. It is 1.6 into 10 raised to minus 8 ohm meter. So silver is the best conductor of electricity. So that's all for today. We have discussed 3 portions of the questions. Go through it, make the notes and ask your doubts. Till then, bye bye.